As I mentioned, the radiation temperature has been decreasing as the universe expands. And today this radiation is coming to us from all directions with a temperature of about 2.73 Kelvin. And we call this the cosmic microwave background radiation. Now, as I said, when we go to earlier times, the temperature of radiation was higher, which means there would have been an epoch when the temperature of radiation was high enough to ionize matter. In other words, today most of the matter in our immediate surrounding is in the form of neutral atoms. But if we bombard it with high energy radiation, then this can be dissociated into its constituent particles, nuclei and electrons. And a mixture of this is called plasma. So it means that at early enough time, the radiation energy was high enough to sustain matter in its ionized form. And the matter at that epoch was in the form of plasma. As the universe expands and radiation temperature comes down, then at a certain epoch, the temperature is not sufficient. In other words, the energy in the photons is not sufficient to sustain matter in an ionized form, and these ions make a transition to neutral atoms. Now this transition from plasma to neutral atoms is an important phase in the study of cosmology in general and the cosmic microwave background radiation in particular. The transition from ionized to neutral phase is governed by the celebrated Saha ionization formula. Here X is the degree of ionization, that is the fraction of particles which are in the ionized form, and chi here is the ionization energy. For example, the ionization energy of hydrogen atoms is about 13.6 electron volts. In other words, you have to supply this much energy to completely dissociate the hydrogen atom into free proton and electron. If I plot this function as a function of the degree of ionization and temperature, then at very high temperature, the degree of ionization will almost be 100%. X will be equal to very close to 1. That is because the energy is high enough to sustain the matter in the ionized form. At low temperatures, clearly the degree of ionization will be almost 0. Since with the increase of temperature, rather with the decrease of temperature, time increases, I can plot the degree of ionization versus time. At early times, during the early phase of the universe, the temperature was high and the degree of ionization was almost 1. And at late phase, the temperature was low and it was almost 0. The interesting aspect is that this transition, although is not a step function, is a fairly sharp transition, and because of it I can define an epoch which I call the epoch of recombination. Combination of ions to form atoms, and this epoch of recombination is an important epoch in the history of the universe. So now let me describe what is the effect of that. Here I have plotted time and here I have plotted space. This is a schematic depiction. Need not go into the details of that, but all what we want to know here is the following. At early times, matter was ionized. It was in the form of charged particles, and we know that particles of light significantly get scattered from charged particles. And so the motion of light, particles of light called photons, is that of a random walk. This situation continues till an epoch when the universe became neutral. Once it became neutral, charged particles can travel without being hindered. And so the net effect of this is that today we will perceive that we are receiving photons from a certain distance at the epoch of recombination, that is the epoch when ions combine to form atoms, and so it will appear as if there is all the micro background photons are coming to us from a certain distance. In this two-dimensional space, this will be a circle, but in the real case of a three-dimensional universe, we will feel that these photons are coming to us from a spherical surface in the center of which we are located. And so this is the cosmic micro background radiation which is bombarding us. And so this is going to be our perception that here the photons are random walking, but once beyond this epoch, they will all be coming to us from all directions. Now, this study of microwave background has progressed quite a lot in recent years. It is primarily seen that this radiation density is uniform here, so it is an isotropic radiation coming to us. However, there are some non-uniformities on this, and these produce a number of interesting effects like anisotropy of radiation, polarization of radiation, something called spectral distortion, which is actually a topic of more advanced stuff. Here I will conclude by saying the following, that the study of microwave background radiation has progressed a lot, not only on theoretical but also experimental level. And the next slide shows the experimental progress which has been made in this study. So here I will compare two pictures. One is from an experiment called Kobe, which produced the results in 2003, and the other which produced the result in 1992, and other WMAP which produced the results in 2003. And the improvement which has happened in these 11 years. So this was the kind of picture which Kobe saw of the microwave background. Blue regions are low temperature and the others are the higher temperature. And what WMAP saw was the following. You see the increase in resolution, drastic increase in resolution. As a comparison, let us see one picture. And in this picture, we can hardly make out what is here. And now let us see if the same improvement was done on this picture, what we will see. So you clearly see a child, and you can even see the band on its hand. So this is the degree of improvement which has happened in 11 years in this field, and this field is continuously progressing, and even recently there has been the first results from the Planck satellite, and we have a lot to look forward to.